Hi folks, welcome to this lesson on integrating functions of the form f of ax plus b. We already have simple rules for anti-differentiating f of x, and we'll take a look at those. Here they all are. These are really the main ones for us. We can use the circle of trig. The problem is, if we don't just have, say, e to the x, if we have e to the 2x, there may be some issues that crop up from the chain rule, and we check by differentiation. So when we integrate something like e to the 3x plus 1, you might be tempted to write e to the 3x plus 1. And if it's an indefinite integral, well, you put a plus c. By checking with differentiation, though, let's see what would happen. We'd get, when we differentiate this red one, we'd get e to the 3x plus 1 times 3 because of the chain rule. So by checking with differentiation, we can show it's incorrect. To account for the 3x that's in the original function, we need to fix this by putting a 1/3 out front. So because it ended up being too big by a factor of 3, we put a 1/3. A similar approach needs to be taken when integrating any function of this form, f of ax plus b. Basically, we proceed as usual, but we make sure we include a correcting coefficient of 1 over a in our answer. And that's to fight the chain rule. You should always check your integration through differentiation. Like always. I am yelling this at you. Make sure that you do it. Because you're always going to be better at differentiation than integration. I am too. To show you what this technique looks like in motion, I'll do a few examples with no particular approach. All I'll do is say sine anti-differentiates to negative cosine. So I think that the indefinite integral might be negative cosine of 3x plus 2, and I'd need a plus c. And then I will check with differentiation. Now I know that negative cosine goes to sine, and I'd get sine of 3x plus 2, and then from the chain rule I'd get a times 3. I'd say, oh no, it needs to be 1/3 as big. So there needs to be a negative 1/3 in front. The negative because of the cosine, and the 1/3 because of the 3x in 3x plus 2. And when I check that, well, now it'll be okay. I'll be back where I started. Sine of 3x plus 2. Let's try another one. It's got something on the bottom, so I think that it's going to turn into ln of 7x plus 5. Or maybe I should write that as absolute value of 7x plus 5 if I really want to get specific about it. Plus c. And now I'm going to check. So I'd get original on the bottom, derivative on the top. Oh no, it's too big by a factor of 7. So what I need out front, I need a 1/7. Now you might notice that to begin with just because of that 7x in there. But if you don't, you'll pick it up just by checking. Same sort of idea with this last one. I'll think the power will need to go up by 1, and the flip of the new power comes in front, a plus c, and I can check that by differentiating. So I'll get 1/3 times 3 times 4x plus 3 to the power of 2. And then I'll also have the chain rule give me this 4. And you can see these will divide out, but it's still too big by a factor of 4. So I need a 1/4 out front to fix that. And maybe if you notice that the 4x is going to cause you a 1/4, then you can end up avoiding this sort of check being necessary. But you should always do it anyways. Otherwise, it's just hubris. Okay. And then we end up with 1/12 4x plus 3 cubed plus c. And we've already basically checked that that one's okay. So what does that look like as a method? Well, here's a set of rules that can basically be summarized by the integral of some function of the form f of ax plus b dx is going to be the antiderivative of ax plus b with a plus c, but you need a 1 over a out front. And there's a full set of rules here. I think that's a lot to memorize, though, especially since this is really essentially a middle way. It's a special case where we happen to be doing a function on a linear, But you may end up with situations later where it's not just a linear, and substitution ends up being a much more full-service approach that deals with this and tougher stuff. Here's my method for people with brains that are already full. Integrate the function, put a 1 over a out front if you remember, check using differentiation, and if it's not quite right, if it's off by some factor, fix it if necessary. Use the factor by which your result is too big or too small. So we'll go through a few where we use this technique, but if we botch it, then we'll always be able to fix it up. This first one, we've got a linear to a power, so the power is going to go up by 1, and that means the flip of the new power goes in front, and also because of that 2x in the brackets, I'm going to multiply by 1 over 2. So we'll get 1/10, 2x plus 3 all to the 5th, plus c, and then I'll check that. Okay, so I'll get 1/10, the 5 will come down front, the power will go down by 1, and then from the chain rule I'll have times 2. So that's 10, and the 10 divide out. Yay, we're back where we started. This next one, I probably want to rewrite it in exponential form. So it's to the power of -1/2. And so same sort of idea. The power goes up by 1. The flip of the new power goes in front. But also, I need to take the reciprocal of this coefficient of x. So this would be an easy one to miss. So I have a -1 over 2 times that whole thing. And then I have my plus c. So that'll give me -1 minus 2x to the half plus c. Okay. And I can check with differentiation. That'll give me negative. The half will come down front. 1 minus 2x to the -1/2, and from the chain rule times -2. In other words, I'll end up with 1 minus 2x to the -1/2, which is what I started with. I think this is an easy one to botch, so I just want to show you how you might do it if you didn't notice all this stuff. I would bring my power up by 1. I put the flip of the new power in front, and I'm sort of wondering, is that my answer? And then I'll go ahead and I'll try and differentiate it. So it'll be 2 will stay, and then the half will come down front, and the power will go down by 1. And then from the chain rule, I'll have a -2 here. So what will happen? This 2 and this half will multiply out, and I'll end up with this, which is too big by a factor of -2. What does that tell me? That tells me that I need a -1/2 out front here that I multiply by. So getting the wrong answer helps me on the path to getting the right answer. And then I can just simplify. We'll try and use the rules in the next one. So 2 is going to stay. E to the 2x becomes e to the 2x, but because of that 2x, we need a 1 over 2 out front. Minus e to the -3x is going to be e to the -3x, but because of that -3x, we need a -1/3 out front. And again, if you don't notice this stuff, just give it your best guess, and then see if you can fix it. Plus 1/3 e to the -3x plus c. I think that's the answer. Let's check. It would give us e to the 2x times 2 from the chain rule, plus 1/3 e to the -3x times -3 from the chain rule, or 2 e to the 2x minus e to the -3x when we check, which is what we should have. This last one is kind of tricky. It looks like b, but when you don't have an exponent, maybe you're tempted to write it like this. Maybe you're tempted to write this. And then power goes up by 1. One thing to notice about the power rule is that it does not work when n is -1. Instead, you're in this case over here. So the indefinite integral is going to involve a logarithm. Instead of rewriting it like this, here's what I'm going to do. I'm going to rewrite it so that I can see that 4 is a coefficient. and then 1 over 2x minus 1 dx. So if I'm just guessing this, here's what I'll do. I'll say it's going to be 4 times the ln of 2x minus 1 with absolute values plus c. And then I'll check. I'll get 4 times original on the bottom, derivative on the top. I'll get 8 over 2x minus 1. That's not what I started with, so it's too big by a factor of a half. So this really needed to be multiplied by a half here. And we actually knew that because there was a 2x involved. So that we always have to take that factor of the reciprocal of the coefficient of x if we happen to remember, or we just try our best, see if it works, and then fix it. Okay? Here, if you check, it's going to work out. One last one. Let's see if we can do this according to the rules. So 2, maybe I want my wheel of trig here. Sine goes to cosine, goes to negative sine, goes to negative cosine when we differentiate. But when we anti-differentiate, I'm going to get negative cosine of 3x. But because of that 3x, we need a 1/3 here. So there we go. There's a negative 1/3. On the other one, the antiderivative of cosine is sine. So I'm going to get sine, not cosine, but sine of 4x plus pi. Remember, pi is just a constant. And because of that 4x, I'm going to need a 1/4. Let's see what happens when we simplify a little bit. That'll give me negative 2/3 cos of 3x plus 1/4 sine of 4x plus pi. Okay, and I should have had some plus c's here. So there they are. And we'll check. What will we get? We get negative 2/3 times the derivative of cosine is negative sine, because we're going clockwise in this case, of 3x. Then from the chain rule, times 3, plus 1/4 derivative of sine is cosine, 4x plus pi, and this kind of in brackets here, times 4. That would give us 2 sine 3x plus cos 4x plus pi, which is back where we started. So we must have done it correctly. This is the correct answer. Honestly, the more informally you can do these questions, probably the better. If you have a really good understanding of differentiation, and you feel like you can just sort of reverse hack it, then fantastic. Just do that and don't apply any rules at all. If you feel instead that these rules are going to be helpful, go for it. But either way, make sure that you check. There are some practice questions over here in the Oxford textbook. I hope this has been helpful. Good luck with the material, folks, and take care.